Dr. Nelson, it's so good to have you with us.
Thanks for having me.
Now, you're a professor at Biola, and you're also a fellow at the Discovery Institute.
That's right. So I commute to Seattle and Southern California.
And yet you live in Chicago. I think that's amazing. But listen, today we're going to think little. We're going to talk about the single cell.
Yes.
Now, just to help me, what we know about the cell today compared to what Darwin knew when he wrote his theory has changed a good bit, hasn't it?
Boy, that's putting it mildly. You could say that we're in a completely different universe of understanding. For Darwin and the evolutionary thinkers of the 19th century, the cell was kind of a black box. They didn't really know what was going on there. They didn't have a theory of heredity that we have today. They didn't understand about the molecular machines that actually run the cell. So I like to ask, what would happen if we could bring Darwin back and just show him what's there in something that he thought was actually probably pretty simple.
And it's not simple at all.
No. In fact, if I had to pick one argument that I thought really supported the truth of intelligent design, that showed that living things were the product of a mind, I would take people through how a cell works, because it's just so beautiful and so elegant and really breathtaking, ultra high-tech.
And so what dimension of the cell are we going to look at today?
Well, we're going to ask a question that's really more general, and that is, how simple can a cell be and still exist?
All right.
Can you keep going down all the way to chemistry, or do you reach a point at which, if you want a cell, you've got to have a certain amount of hardware? So let's take a look at our theater in which our drama will take place. There's our question: what does an organism need just to survive? So this is our theater, if you can call it that. And on the bottom, down here, you're unquestionably dead. Okay, so that's the asphalt in the parking lot outside. Up here, you're definitely alive. That's you and me, the E. coli in our large intestine. Then you've got this kind of funny zone here in the middle, where as you approach the living state, you can get more and more complicated. So there are some very complicated viruses that are right here, just below that threshold point. But technically speaking, they're not alive because they can't survive without another cell. They don't have the right equipment to make a living. The main approach to this problem from an evolutionary standpoint has been bottom up. Now, the reason for that is that once upon a time, on the evolutionary theory, there were just chemicals and no cells. Then, at some point in Earth history, that chemistry got together. The process is unclear, but a living cell emerged. So the idea of going bottom up is to try to recreate what evolution itself did once upon a time. But there's another way we can come at the problem. Well, first let me say this about the bottom-up approach. You can think about this like looking for the recipe for the living state, where I give you A, B, C, D, just like the ingredients in a recipe. You put those together and
you make life.
You make life. That's what they're looking for. They haven't found it yet. So that section there in brackets indicates a whole lot of stuff that's got to be put together. But that's the basic analytical approach. Get the parts together, provide some energy.
We just don't have quite the right recipe yet.
Don't have the recipe
We're going to
yet.
make life any day now.
Someday.
Okay.
Someday. Now, this animation shows the idea, you're putting the pieces together, and if all goes well, you bootstrap into life. That's the bottom-up approach. Now, you can also come at the problem from the other direction. Top down, you start with a cell and you take things away. So it's a subtractive analysis.
So this cell's alive, and how many things can you take out of there and it still stays alive?
Still stay above that line.
Okay.
Stay alive in culture, grow in the lab. This is subtractive. Now, here's a kind of grisly thought experiment, but it'll illustrate the point. Let's suppose I went to a hospital nearby and was put under an anesthetic and wheeled into an operating theater. And when I came out of the anesthetic, my left arm was gone. Now, I'd be very unhappy and let people know how unhappy I was, but I would certainly be alive. Okay, same scenario, same operating theater, but this time the surgeon cuts through my brainstem.
Ouch.
Right back here, all the way through where the respiratory control centers are. It doesn't matter what else is right with me, it's over. So you can see that the parts of our biology aren't all equally important for function. You know, you can get by without a lot as long as you've got your essential equipment. So this kind of subtractive analysis says, what's on the parts list that we can't do without? What are the pieces that that cell absolutely needs for function? So top down, we start with a living cell, and we say, well, you didn't need that. You probably didn't need that, but take away something else, you crash the whole system. So there's our theater in which our little drama will take place.
Okay.
Now, let me go to the board.
Okay. Appreciate that.
Or should you have asked me?
Climb every mountain. Here we go.
Here's another way to think about it. Let's say this is a mountain in Switzerland, and we want to put a road through there, a tunnel. Here in Pittsburgh, there are lots of these. Well, you know that if you're going to tunnel from the north and tunnel from the south, these two crews have to be in communication with each other. In order for that tunnel to function, it's got to meet in the middle.
Yes.
Well, we can go back to our scenario. In order for the bottom-up approach really to work, it's got to match what top-down analysis tells us.
Sure.
So if unassisted chemistry only gets you a little way towards that threshold, that can't have been how life came to be. In order for evolution to work, bottom-up unassisted chemistry must be able to give you enough complexity that where you're meeting what your top-down analysis tells you you've got to have. All right, let's look at the most widely accepted bottom-up approach right now in evolution. It's called the RNA world hypothesis. And the RNA world hypothesis tried to solve a deep chicken and egg problem in the origin of life. Looks like this. DNA is the main information storage molecule in all life that we know. It's actually remarkably stable chemically. It's a good way to store information. The problem with DNA is it's chemically inert. That is, it can't do much for you in the cell. It's a library, but the cell needs actors,
Right.
machines that will do things. DNA codes for those machines proteins. Most of the important biochemistry in the cell is performed by these molecular players. But here's the problem. To get the information out of DNA, you need proteins, but you need DNA to code for those proteins. So you get this closed-loop relationship where both entities are necessary for function, but neither will do it on its own. For a long time, origin of life researchers looked at this and said, how are we going to break through that closed loop? Looks like we need a whole lot of complexity all at the same moment. Well, RNA seemed to solve the problem. Because RNA, like DNA, can store information. It's a nucleic acid. But, unlike DNA, most RNA in the cell is single-stranded. And it can fold up in interesting shapes like this and perform catalytic and enzymatic functions. So it can be both a tape, information storage, and a shape that will do things for you. So in a single molecule, it looked like they had the solution to that chicken and egg problem. Because if you can get one of these that will make copies of itself, something like natural selection can begin to operate and refine the process or refine the molecule. The RNA world hypothesis says the first self-replicating entity was not a whole cell. That'd be way too much complexity all at once. Rather, it was a single RNA molecule capable of self-replicating. You isolate that in a membrane, and you got the evolutionary story up and running. So that's the hypothesis in a simple form. We go back to our theater. There's our self-replicating RNA heading towards the living state. Now, even though this is the most widely accepted hypothesis right now, it has a lot of skeptics. Here's one, Stuart Kauffman. He's an origin of life researcher. I mean, that's among the things that he does. He's actually a very wide-ranging thinker. And he works on the problem at the Santa Fe Institute and also at the University of Calgary. He's a skeptic, though. He doesn't buy it. And he doesn't buy it for a very interesting reason. He says, look, there are lots of problems with this story, this RNA world hypothesis, but there's one that's most rarely talked about. Now, he calls these RNA molecules nude replicating RNA molecules, meaning that they're not a whole cell. They're just a single, folded up RNA that can do interesting things, in particular, make copies of itself. He said there's a problem, though, that's insurmountable, and it's rarely talked about. All living things seem to have a minimal complexity below which it is impossible to go. So, when we started, we talked about how much can you take away. Kaufman is saying it looks like there's a point at which you bump into a barrier, a lower threshold below which you're dead. So if you look at it this way, he's saying subtract, subtract, take away parts, and all of a sudden you find a point you can't get below that, because if you try, it's over. Now, the interesting scientific question is, how low is that threshold? Where is it? Kaufman goes on, he says, all free living cells, something you can grow in a lab, seem to have at least the minimum molecular diversity of Pleuromonas. Now, that's a generic name for a particular kind of bacteria that I'll show you in just a moment. Your antennae should quiver a bit here. I like that phrase. He says, you need to pay attention. There's Pleuromona. This is actually the Linnaean term, genus Mycoplasma. These are very stripped down cells. They frequently infect the epithelial lining of our airway and also our genital tract. And they're so stripped down that they're very hard to keep alive in a lab. For instance, they can't make any amino acids for themselves. They've jettisoned all that molecular hardware. So when you grow these in culture, you need to provide them with like a really rich buffet of nutrients, amino acids, cholesterol, you name it. They need it to grow in a lab. But they are free living, and even though they have only about 500,000 base pairs of DNA, they provide a pretty good model for a simple cell.
It's about as basic as it gets.
You can't get much
alive.
simpler.
Yes.
Really stripped down. You can't get much simpler. So anyway, Kaufman says, it looks like something like this is close to that lower threshold. Question is, how much can we take away from Mycoplasma and still have a functional cell? So Kaufman says, your antennae should quiver a bit. Tune in. There's something interesting here. As he puts it, why is there this minimal complexity?
And you're going to answer that for us when we come back. We have to take a break right now, but we're down to the basics. It doesn't get any more basic than this. You'll want to stay with us. Don't go away.
Today's guest on Origins, Dr. Paul A. Nelson, Ph.D., is a philosopher of biology and evolutionary theory. Dr. Nelson is currently a fellow of the Discovery Institute and adjunct professor in science and religion at Biola University. Paul lectures frequently regarding the intelligent design debate at colleges and universities throughout the U.S. and Europe. He has appeared in several films on intelligent design for Illustra Media. One video he would like to make available is titled Metamorphosis. To order the DVD, call 800-266-7741. To contact Dr. Nelson, write to Biola University, 13800 Biola Avenue, La Mirada, California, 90639.
We are back with Dr. Paul Nelson, and we're talking about the simple cell and how simple can a cell be and still be alive. Now, when we left, you were talking about Dr. Stuart Kaufman, and you said that he said, why is there a minimal complexity? Can you help us with that?
Yeah, it's an interesting question, both from the scientific standpoint, but also almost from a philosophical standpoint. But let me give you an illustration, a story that helps people, I think, to see what's going on. In the novel Around the World in 80 Days by Jules Verne, there's an episode as Phileas Fogg is trying to get back to London, across the Atlantic, and he hires a steamship in New York to carry him. Well, about two-thirds of the way out into the Atlantic, they run out of coal. And the captain comes and says to Fogg, we're in trouble. Fogg says, well, tell you what, I'm going to buy the ship. And he does. He buys the ship, and his first command as the new owner is to tell the captain, burn everything inessential. So in go the deck chairs, in go the beds. Even Henrietta, the figurehead of the boat, goes in. The captain doesn't like that, but she goes into the boiler as well. Now, they keep it moving, heading towards Liverpool, but there's a point at which there's nothing left to burn. Everything that's on that boat needs to be there to perform that function of getting across the
They've
Atlantic.
stripped it down to the absolute essential. It's still a boat, still floats,
Still moving.
but you can't burn anything else.
Can't burn anything else.
And what we're really saying is, where is that point in the cell?
Where's that point in the cell? How much hardware do you need to perform the basic functions of metabolism, growth, cell division, and so forth? And it turns out that that point is actually remarkably high. There's a lot of hardware that you need. But there's another way of getting at this question that I'd like to try, and it's really kind of a thought experiment. Imagine that we're exploring a planet, somewhere else in our Milky Way, in our galaxy, and we see little entities that are multiplying and making high-fidelity copies of themselves. So you can see them there along the bottom of the screen.
Okay.
They may not have DNA, they may not have RNA. Who knows what their biochemistry is? But they're making these high-fidelity copies, and they look for all the world like living things. So we take one back to our ship. There it is, this green little blob. And we notice that it's doing a lot of interesting things, such as it is transporting across the boundary between itself and the environment in a selective way. I mean, you think about yourself. You don't put just anything in here, and you don't put just anything out in terms of waste. There's a selective transport that all living things do between themselves and the world.
Got it, okay.
We notice that it's converting energy. Takes in raw materials, converts them into the form that it needs. It's storing and replicating information. So I would say that if you saw something like this, even before you examined its biochemistry, that entity was performing all of those functions, you'd say that's a living thing.
Would sound that way to me.
Yeah. So I think we recognize the living state first in terms of its functions. Now, here is going to be an interesting puzzle. How much of this can we take away, even before we talk about the hardware, and we'll do that in a later program, but how many of these functions can we take away and still have a viable cell? Now, there's one here that arguably you don't need. See if you can figure out which one it is. I'll give you a clue from my own life. It's March 16, 1992, Beth Israel Hospital in Boston. My wife is lying there getting ready for a C-section. At that moment, my daughter Hannah was born. She's 20 years old now. At the point of reproduction, my wife and I had successfully passed on genetic information to another generation.
Okay.
But I was, in my early 30s. From 0 to 30, I was unquestionably alive. So the one that we can arguably do without
It's reproduction.
is reproduction.
Okay.
That's the one that you could say isn't necessary. Unfortunately,
You
now
can be alive and not be reproducing.
you can be alive and not be reproducing.
Gotcha, okay.
Now, unfortunately, this cell now has got to live forever. It's lost the ability to replicate. Okay, that was the only one we could really argue about. Now watch what happens. Let's suppose we take away transport. What's going to happen to our entity?
Well,
It can't
either feed itself or get rid of waste.
get rid of waste. So it's either going to starve to death or explode.
Yes.
As long as it's still metabolizing and producing waste, it's
Right.
got to have a way to get it out.
Okay.
Now, even though it may be alive for a little bit longer, it's going to go rapidly downhill.
Right.
Okay.
Can't live very long like that.
It can't live very long like that.
Yeah.
Let's take away information replication and information storage and transfer. All living things, to make the molecular pieces that they need to function, keep a library in DNA. Now this hypothetical creature might keep it in some other molecule, but on this planet we keep the information in DNA because that's kind of the hard copy that we're going to make the individual players from. Once that's gone, we don't have any archive of information to draw on to build the molecules that will function in metabolism or energy conversion. Now, we've lost those functions as well because we can't make the parts. Take those away, that's a bubble. That's not a living thing.
It's just got a cover over it and there's nothing inside.
Yeah.
Yeah, okay.
6 feet down, put up a tombstone. It's over. What you can see just from this analysis, even before we talk about the actual molecular players, which we'll do in a later show, if you just consider how functions relate to each other in a cell, they're all interconnected in a really complex web of relationships. So take one away, eventually you lose them all. What this means is In order to have a cell at all, you need a lot of equipment present at the same moment in time
Right.
for the living state.
What's the implications of that to the evolutionary debate?
I think it tells, or it should tell, an evolutionary biologist, if you're trying to build these entities bottom up,
Yeah.
starting with basic chemistry, recognize that the target that you have to reach, that threshold of the living state, may not even be, down the road or in the next county. It's in another galaxy. It's so far off that you need to rethink the assumptions that you've made about how cells came to be.
There's so many pieces that have to be there at the same time.
At the same time.
That you can't gradually get 2 or 3 of them while you're adding anymore.
That's right. And in fact, the chemistry goes in the other direction. You take a little piece of hamburger and leave it in a glass of water on your kitchen counter. Come back in several months, there's not going to be any hamburger there.
It doesn't get better.
It doesn't get better. The water will attack the peptide bonds in those proteins, and they're going to head towards basic chemistry,
Right.
not the living state.
Irreducible complexity, is that a fair term or is that a wrong term?
No, that's the right term. And I think what we see here is irreducible complexity at the scale of the whole cell. That the living state itself requires so many components. In effect, you can subtract a few, take a few away, but then you quickly discover everything else is essential. Just as it was in that Jules Verne story, you can burn the deck chairs, there comes a point you can't burn anything else.
I'd like to ask you this question. Sometimes when I talk to materialists, they say, how can you base your whole life on an old book that's out of date? But sometimes when I hear evolutionists talk, it seems to me that they're basing their whole life on a theory, a 19th century theory that predates the scientific evidence we now are using, and it seems to me that they're going to extraordinary lengths to try to validate a theory that seems very much out of date. Does that seem that way to you?
I think there's a lot of truth to what you say. And in my eyes, the real problem is the philosophical foundation of the theory, which says if you're going to do science, you're restricted to a toolkit of just material physical causes. We know that can't be adequate, though. Just look around you. The people watching this program, for instance, are watching it on devices that require intelligence for their very existence.
Right.
And I think intelligence is real. It's part of the universe. It brings about effects that can only be explained by reference to a mind or intelligence. And a healthy science will use all the possible causes at its disposal, not setting some aside, saying we're not going to use those, we don't like the implications. Science needs to move forward, and if we've inherited a bad philosophy of science from the 19th century, as I think is the case right now, we need to get rid of that and try something better.